Hello and welcome to Honors Function. This is the fourth lecture on this second unit about polynomial and rational function. And in this lecture, we're going to introduce polynomial functions. So this lecture mostly settles the terminology and the notation about polynomial function. There are no new results, except we're going to review some old formula about expanding and factoring polynomials. Let's begin. So let's start by looking at two examples of some polynomials. So a polynomial is a sum of monomials. What do we call a monomial? Well, this is a monomial, that's another one, here and there. So this first polynomial right here is a sum of 5 monomials, right? And these are called terms, but more precisely, monomial. So a monomial, for example, let me take 2x4 right here. That's this one, the second one. 2x4. This is called the coefficient of the monomial, and this is called the degree of the monomial. The degree, what is the degree? The degree is an element of n. The degree is an element of n, meaning can be 0, 1, 2, or any counting number. The degree cannot be z, okay? The degree, if you are a monomial, the degree cannot be a negative number. For example, this is not a monomial. This is not a monomial, okay? The coefficient is just a real number. So this is what we call a monomial. And if you add monomials together, you find a polynomial. What do we call the degree of the polynomial? The highest degree of its monomial. So we have 5 monomials right here. Oh, let's take a look at this one right here. Is this a monomial, -5? Yes, it is. Check it out. It is -5 times x to the power of 0, right? And my exponent is actually in n, and this is actually a real number. Therefore, this is a monomial, all right? So, monomial of degree 0. This is a monomial of degree 1, degree 2, degree 4, and degree 5. What do we call the degree of the polynomial? The highest degree of its monomial. Here, it's a degree 5. This term right here, this monomial, this term, is called the leading term. Okay? If you look at the monomial of highest degree, you call that the leading term. And this coefficient right here, this is called the leading coefficient. All right? Now, the monomial of degree 0 right here is called a constant term. This is called a constant term. It doesn't change with x, right? It doesn't matter what x is. This is going to be constant. It doesn't multiply x, all right? Let's look at the second polynomial. This is a sum of 3 monomial. The degree is 3, right? The leading term is x cubed. The leading coefficient here, the leading coefficient is 1. What's a constant term? What's a constant term? Well, what's a constant term? It's the monomial of degree 0. Where's the monomial of degree 0 right here? You don't have it, so it's like 0 times x to the 0. So it is 0. The constant term is 0, okay? All right, well, with that in mind, we can now generalize this polynomial. And the way to write a generic polynomial is this way. This is the way I'm going to write it. I'm using subscript notation. an x to the n plus a n minus 1 x to the n minus 1 plus a n minus 2 x to the n minus 2 plus etc, 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 plus, okay, what are my last one? a2x squared plus a1x plus a naught. a0, this is called a naught. Not a n a-u-g-h-t. Okay, a naught. All right, this is a0 right here. I'm using subscript notation. Why not use letter? Because how did I write the quadratic polynomial? I wrote it like that. ax squared plus bx plus c. Why did I not use subscript notation? Because I only had 3 coefficients, right? If you want to use subscript notation here, you can, and it would be a2x2 plus a1x plus a naught, right? That's how you would write it using subscript notation. But you don't need to. It's not common to use subscript notation for that because we only need 3 letters, okay? How would you write a linear polynomial? This is a quadratic polynomial, right? You know that. Quadratic polynomial. How would you write a linear polynomial with subscript notation? a1x plus a naught. Okay, but we don't write it like that. But in general, a generic polynomial is written like this, and we don't write a, b, c because we don't know what the degree is, okay? So this is called the leading term. N is the degree of the polynomial, and I will write that deg of, if we give it a name as f of x and that becomes a polynomial function, we would say the degree of the function f, okay? An is the leading coefficient, okay? Don't confuse the leading term with the leading coefficient. And a naught is a constant term. f0, f of 0 right here, is just a naught. And this is called the initial value, okay? I guess it comes from physics right here. This is called the initial value of the polynomial. Finally, so let's take f of x equals anxn plus a1x plus a naught. Okay, we don't normally write all the one in between right here. Like, I don't need to write n minus 1. I know they're there. If there is a real number, let's take a real number, for example, alpha in R, such that f of alpha is equal to 0, well, alpha is called a root of f. It's called a root of f, okay? A root of the polynomial function, actually, we all sometimes say a root of the polynomial function f of x. What is a root of the polynomial function f of x? It is a solution. A root is a solution to the equation f of x is equal to 0, right? And so when we're going to be thinking about the graph, it is related to the x-intercept of the graph, of course. There will be, although, a slight difference between the root and the x-intercept sometimes, and we're going to have to understand that. A root is not always an x-intercept. An x-intercept is always a root, but a root is not always an x-intercept. Now, maybe some of you think they have the answer there. Why? I will answer that in a later lecture, okay? So a root, a solution to the equation. Oh, I didn't write my equation. Yeah, a root of f of x, a solution to the equation f of x equal to 0, or an x-intercept of the graph, same thing. All right? Okay, let's go over the first example now. So here is the first example. What is the leading term, the degree, the leading coefficient, and the constant term of this polynomial? So this is not written in standard form. Standard form is when you write all the coefficients like that, right? All expanded, an minus 1, xn minus 1, in decreasing order, plus a1x plus a naught. This is called the standard form of a polynomial, okay? This is not in standard form, it's like factored. This is factored, right? So we need to understand where to get the leading term. So of course, please do not expand. I repeat, do not expand this. It would take you a long time. You would probably make a mistake. I would make a mistake. And we don't need to. You need to understand where the leading term is from. You're multiplying 3 factors. You're multiplying -2 with this factor right here, with this factor right here. The leading term will carry the highest degree. So, what's the highest degree of the first factor? Well, that's just -2. What's the highest degree of the second factor right here? Well, let me get rid of this. Inside the parentheses, the highest degree is -2x squared. But you are cubing it, right? So it's like -2x squared cubed. And I know there's other stuff around, but I'm just fishing for my highest degree, right? I don't care about the other stuff around. And in the last parenthesis, what's going to be the highest degree of the whole term right here? It's going to be -3x cubed squared plus a bunch of other terms which I don't care about. So basically, when everything is expanded, you're going to have this negative 2 that doesn't change right here. Then here it's going to be times negative 8x to the 6. Please make sure you don't make a mistake on the rule of exponent here. They're pretty old. Times, so negative 3 squared is just 9x to the 6 again. So what is this? 8 times 9, 72 times 2, 144. It's a plus, right? 2 minus makes a plus. 144 x 12. All right, that's my leading term. That's my leading term. Out of that, I can get the degree. The degree of the polynomial that I called f is 12. And out of that, I get the leading coefficient. I don't think we have a notation for that. The leading coefficient is 144. That's it. That's it for the first three object I'm looking for. Then I want the constant term. Well, the constant term is pretty straightforward. It's f of 0. So I need to go right here and get f of 0. What is f of 0? So it is negative 2 times 3 minus 0 cubed, right? So 3 cubed. And then times a bunch of 0, like this is 0, right? This was 0 right here. This is 0, 0, 0. And I'm just left with 2 squared times 2 squared. Oops, I said cube, but I wrote squared. So my my constant term or initial value is negative 2 times 27 times 4. That's it. 27 times 2, 54 times 2, 108 times 2, 216, negative 2, 16, I think, if I didn't make a mistake. All right? That's it. This is how you find all this information without expanding. Do not expand. That would be a terrible mistake. Please do number 2. And I think I'm going to ask you to also do number 3. Let's go now for the next part of this lecture. It's all a review. So let me take my notes and look at a couple of formula I want to review. So finally, I've been talking about this formula for a while, and some of them are from algebra. Actually, this is alg 1 right here. This is alg 1, alg 1, alg 1. Okay, this should have been seen in alg 1, and this is a factorization formula from alg 1, and all of the other ones are alg 2 formula. So it's okay if you don't remember them. Okay, it's okay if you don't remember them, but you should at least acknowledge that you have seen them before. All right, now do not confuse expanding formula with factoring formula. Okay, when you expand, you break what's factored. This is already factored. That's factored. That's factored. This is factored, and this is factored. And I'm expanding it all. Okay, I'm writing a factorization as a sum. Okay, so useless to say, you really need to know this formula. Factoring formula, you're writing a sum. Okay, these are sum or differences into a product. Okay, so and as you can see, why don't I have a squared plus b squared? I'm only interested in looking at this formula in R, not in C. In R, you do not factor a sum of squares. You factor that in C, you don't factor it in R. Okay, so they should be all recalled. Let me quickly talk about these right here. How do you remember them, especially the coefficient? This comes from the Pascal triangle. Now, I don't know if this was taught to you. Let me bring it about right here. These are the coefficient of the expansion a plus b squared right here. A squared plus 2ab plus b squared. Now, what are the coefficient of a plus b cubed? Okay, well, keep on going on the side. You drop 1 right here, and then you add these two terms. 1 plus 2, 3. 2 plus 1, 3. And these are the coefficient of a plus b cubed. Now, how do you find the different a and b right here? This is a cubed b0. We don't write b0. And then the powers of a decreases by 1. The powers of b increases by 1. a2, b1, a1, b2, a0, b3. And we could go on like that. I wrote only for cube, but what about for power 4? Well, it's the same thing, except that it gets a bit more challenging right here. So here's 1 on the side right here, and then you just add 1 and 3, 4, 3 and 3, 6, 3 and 1, 4, and then 1. 1 what? 1 A4, B0, so I'm not going to write B0, okay? Then the second one is A cubed B1, A2 B2, A B3, and then A0, so I'm not writing it, B4, okay? And you can go on like that. So now, what about if you have a minus in the middle? What about if in the middle you have a minus right here? Well, that's easy. You start by writing a plus right there. It always starts with a plus. And then you switch the sign. So plus, minus, plus. Plus, minus, plus, minus. Plus, minus, plus, minus, plus. That's it. And for that, with that in mind, you can expand anything you want. It may take you a while, but you can expand anything you want, okay? So don't confuse again expanding and factoring. Let's go over some examples now. In my notes, I go over what you have to do to factor, what's the first step, what's the second step. Hey, listen, this is all practice. Please read it and make sure you understand what I'm saying, but in the end, you have to know how to do it. So let's go over some examples. So, example number 1, and the first series of example is about expanding. So, of course, please right here, I don't want you to do this, okay? I don't want you to do this. You would be wasting time if you were to expand like that. And I know Miss Roshan wouldn't be happy when I say you need to remember some formula, because she doesn't like that. But actually, you do need to remember some formula, Miss Roshan, okay? So, let's expand that. I know my cubic formula, so it is. And plus right here, actually, you would have to do it a third time. Well, good luck with that, guys, okay? Good luck not remembering formula. You would just be wasting time. All right, let's go. So you do a cubed, so 3 cubed. Oh, I have a minus right here, right? So what do we do? Minus 3a squared. So a squared times b, 2x squared. Plus 3a times b squared, 2x squared squared, minus b cubed, 2x squared cubed. Okay? So what is this? This is 27. Careful right here. So we get 3 times 9 times 2, right? Times 2 of that. So 3 times 9, 27 times 2, 54. So minus 54x squared. What do we get here? We got a 3 times a 3 times a 4, right? 9 times 4, 36. 36, and then x squared squared right here, right? X squared squared, that's x to the 4th. And then right here we have minus, so 2 cubed, 8, x to the 6th. Here we go. Here's my expansion. I don't think I've made a mistake, but at the end of this first stretch, lately we've spotted a few mistakes in my video. Please let me know if I did make a mistake. Please do number 5, and let me do number 6, and you'll do number 7. These are just factorization. So the first step in factorization is trying to take a common factor. So right here I do have a common factor. I can take 2 out, 2, and then x cubed. So 2x cubed times what? So 27x cubed minus what? Minus 8. And this actually is a difference of cubes. Now, it is not written as a difference of cubes, but it is a difference of cubes. So how do you write it as a difference of cube? Well, easy. If you need to, okay? If you need to write it as a difference of cube to see clearly, what is it? If I want to write it as a difference of cubes, I need to have a cubed minus another cubed. That's a difference of cubes, right? So how do you write that as a difference of cubed? So this is 3x cubed, right? And this is 2. Okay, so this is my A right here, and this is my B. Again, I hope you have done that before, at least, once or twice, or maybe a little bit more. So 2x cubed times. So you need to know the formula, okay? So it is A minus B, 3x minus 2, times A squared, 9x squared, plus AB, plus 6x, plus B squared, plus 4. And here, don't try to factor that. It won't factor. If you haven't made a mistake, this will never factor, okay? Because actually this is the a squared plus ab plus b squared. That doesn't factor. To factor, you need a 2ab right here, okay, and it would be a plus b squared, but you don't have it in the formula. This does not factor. All right, okay, this will conclude this video. So hopefully after editing it will stand under 20 minutes. Thank you for watching.